One day, Earth will scream, and then it will go silent forever. Not the silence of peace, the silence of absence. No wind, no waves, no heartbeat of a living world. Just a charred cinder drifting through the void, or a frozen tomb of ice and darkness. Today we're going to explore the real scientific scenarios for how life on Earth will eventually come to an end. If you're fascinated by the ultimate questions of our existence, make sure to subscribe to the channel. It helps us reach more curious minds across the universe. Now let's begin. Let me start with the most certain ending we know about. It's written in the physics of stars themselves, and there's absolutely no escaping it. Our sun has been burning for approximately 4.6 billion years. It's a middle-aged star, what astronomers classify as a G-type main sequence star, or more casually, a yellow dwarf. Right now, deep in the sun's core, hydrogen atoms are fusing together to form helium in a process that releases tremendous energy. This nuclear fusion creates an outward pressure that balances against gravity's inward pull. It's a perfect equilibrium, a cosmic dance that has sustained life on Earth for billions of years. But here's the reality that physics demands we face: this dance cannot last forever. Every second, the sun converts approximately 600 million tons of hydrogen into helium. That might sound like it would deplete quickly, but the sun is massive beyond human comprehension. It contains enough hydrogen to maintain this fusion process for roughly another 5 billion years. We're genuinely at the midpoint of our star's stable life. The Gaia spacecraft, launched by the European Space Agency in 2013, has been measuring the properties of over 1 billion stars in our galaxy. Through these observations, combined with detailed computer models of stellar evolution, astronomers have mapped out the sun's future with remarkable precision. What they've discovered is both beautiful and terrifying. As the sun continues fusing hydrogen, the helium ash accumulates in the core. Helium is denser than hydrogen, so the core gradually contracts under its own weight. This contraction actually causes the core temperature to increase, which in turn makes the surrounding hydrogen burn more efficiently. The result? The sun is slowly, steadily getting brighter. This isn't some wild future prediction. It's happening right now. The sun is approximately 10% brighter today than it was when Earth first formed. Over the next billion years, solar luminosity will increase by another 10%. That might not sound like much, but the consequences for Earth are profound. Research published in the journal Astrobiology examined what happens to Earth's climate as solar luminosity increases. The models show something sobering. Within 1 billion years, possibly as soon as 750 million years from now, the sun's increasing brightness will trigger what scientists call a moist greenhouse effect. Here's how it works. As more solar energy reaches Earth, surface temperatures rise. Warmer temperatures cause more water to evaporate from the oceans. Water vapor is itself a greenhouse gas, one of the most potent we have. More water vapor means more heat gets trapped, which causes even more evaporation. It's a runaway feedback loop. The atmosphere will become saturated with water vapor. In the upper atmosphere, ultraviolet radiation from the sun will split water molecules apart into hydrogen and oxygen. Hydrogen, being the lightest element, will escape into space. We'll be slowly, inexorably losing our oceans to the cosmos, one molecule at a time. Within 1.5 billion years, Earth's surface temperature could exceed 373 Kelvin, that's 100 degrees Celsius. The boiling point of water at sea level. Any remaining oceans will boil away completely. The geological carbon cycle that regulates Earth's climate will collapse. Carbon dioxide will build up in the atmosphere with nothing to remove it. Earth will transform into something resembling Venus, a world shrouded in thick clouds of carbon dioxide and sulfuric acid, with surface temperatures hot enough to melt lead. Every living thing we know, from the deepest ocean bacteria to the tallest redwood trees, will have perished long before we reach this point. But that's just the beginning of the sun's transformation. Around 5 billion years from now, the sun will exhaust the hydrogen in its core. For 100 million years or so, the core will contract while a shell of hydrogen around it continues to fuse. The energy from this shell fusion will cause the Sun's outer layers to expand dramatically. Our star will swell into a red giant. The term red giant doesn't quite capture the scale we're talking about. The Sun will grow to over 100 times its current diameter. Its surface will cool to around 3000 Kelvin, which makes it appear reddish, but its sheer size will make it thousands of times more luminous than it is today. Stephen Kane, an astrophysicist at the University of California, Riverside, recently published research examining what happens to planets when their host stars become red giants. He studied an aging star system 57 light-years away, observing planets orbiting a star twice the Sun's age. His models showed that inner planets get consumed as the star expands, but there's substantial uncertainty about exactly where that boundary lies. For our solar system, Mercury will definitely be swallowed by the expanding Sun. Venus almost certainly will be too. But Earth? That's genuinely uncertain. You see, as the Sun loses mass through stellar winds during its red giant phase, its gravitational pull on the planets weakens slightly. This causes planetary orbits to spiral outward. Earth might, just might, migrate far enough to avoid being engulfed. Recent calculations by researchers at the University of Wisconsin, Madison, suggest it's essentially a coin flip. But here's the critical point: even if Earth physically survives, even if our planet avoids being swallowed by the bloated Sun, it won't matter. Life will already be gone. The oceans will have boiled away billions of years earlier. The atmosphere will have been stripped away by the intense radiation. Earth's surface will be molten rock, glowing with its own heat under the bloated red disk of the dying Sun. If Earth does survive the red giant phase, what remains will be a scorched, airless cinder orbiting a white dwarf, the dense stellar remnant left behind after the Sun sheds its outer layers. That white dwarf will be about the size of Earth but containing roughly half the Sun's current mass. It will slowly cool over trillions of years, eventually fading to black. Now, you might be thinking, 5 billion years is an incomprehensibly long time. Humanity has only existed for a few 100,000 years. Surely we'll have either gone extinct naturally or evolved into something unrecognizable, or perhaps left Earth entirely to colonize other worlds. You're absolutely right. The Sun's death won't be humanity's end, because we'll be long gone by then, one way or another. But we're not talking about humanity specifically. We're talking about life itself, the entire beautiful, complex tapestry of biology that has developed on this planet over 3.8 billion years. And there are scenarios where life could end much, much sooner than 5 billion years from now. Some are sudden and violent. Others are slow and inexorable. All of them are real possibilities, grounded in the physics that governs our universe. Let me tell you about one of the most catastrophic events that could befall our planet, something so violent that it makes asteroid impacts look gentle by comparison. Imagine a beam of energy so powerful that it releases more radiation in 10 seconds than our Sun will produce in its entire 10 billion year lifetime. Now imagine that beam pointed directly at Earth. This isn't science fiction. This is a gamma-ray burst, and it represents one of the most terrifying extinction scenarios the universe can throw at us. Gamma-ray bursts were discovered completely by accident. In the 1960s, the United States was monitoring Soviet nuclear weapons testing through a network of satellites called VELA. These satellites were designed to detect the gamma-ray signature of nuclear explosions. What they found instead were mysterious bursts of gamma radiation coming from space, flashes that appeared randomly across the sky and then vanished. For decades, astronomers debated what these bursts were and how far away they occurred. The breakthrough came in 1997 when the Italian-Dutch satellite Beppo-SAX detected a gamma-ray burst and, for the first time, astronomers managed to observe its afterglow with optical telescopes. What they discovered was staggering. The burst originated from a galaxy over 6 billion light-years away. Think about what this means. If we can detect these events from 6 billion light-years away, the amount of energy they're releasing is almost beyond comprehension. We now know, thanks to observations from NASA's Swift telescope and the Fermi Gamma Ray Space Telescope, that gamma ray bursts are the brightest electromagnetic events known to occur in the universe. There are two main types of gamma ray bursts. Short-duration bursts, lasting less than 2 seconds, are thought to result from the merger of two neutron stars or a neutron star colliding with a black hole. Long-duration bursts, lasting anywhere from 2 seconds to several minutes, are associated with the deaths of massive stars. Let me walk you through what happens when a massive star dies. We're talking about stars at least 20 to 30 times more massive than our Sun. These stellar giants burn through their nuclear fuel much faster than smaller stars. When a massive star exhausts its fuel, there's no longer any outward pressure to counteract gravity's inward pull. The core collapses in less than a second. The collapse is so rapid and violent that it overshoots equilibrium. The core compresses to nuclear densities, then rebounds like a spring. This rebound drives a shockwave outward through the star's outer layers, tearing it apart in what we observe as a supernova. But in the most massive stars, something even more dramatic happens. The collapsing core doesn't stop at becoming a neutron star. It continues collapsing into a black hole. As material swirls into this newly formed black hole, it forms an accretion disk. Magnetic fields in the disk twist and concentrate the infalling material, channeling it into two narrow jets that shoot outward from the black hole's poles at 99% the speed of light. These jets plow through the outer layers of the dying star, breaking through the surface and extending out into space. When they do, they generate gamma rays through a process involving relativistic particles and intense magnetic fields. The jets are narrow, typically only a few degrees wide, like cosmic lighthouse beams sweeping through space. Here's the crucial point: we only detect a gamma ray burst when one of these jets happens to be pointing directly at Earth. For every burst we observe, there are hundreds more happening throughout the universe that we never see because their jets are aimed in other directions. Now, what happens if a gamma ray burst occurs not billions of light years away, but right here in our own galaxy, close enough that Earth falls within the beam? A research team led by Adrian Mellett at the University of Kansas published a fascinating paper examining gamma ray bursts as possible causes of mass extinctions in Earth's past. They calculated that a gamma ray burst occurring within several thousand light-years of Earth could have devastating consequences for our biosphere. The gamma radiation itself would arrive first, traveling at the speed of light. These high-energy photons would slam into our atmosphere, specifically the stratosphere, where most of Earth's protective ozone layer resides. Gamma rays have enough energy to break apart molecular bonds. They would shatter nitrogen and oxygen molecules, creating highly reactive nitrogen oxides. Here's where it gets terrifying. Those nitrogen oxides would rapidly catalyze the destruction of ozone. Within weeks to months, up to 50% of Earth's ozone layer could be depleted. Some models suggest the depletion could be even more severe, approaching 70 to 80%. Ozone is crucial because it absorbs harmful ultraviolet radiation from the sun. Without it, UVB radiation reaching Earth's surface would increase dramatically. This radiation damages DNA, causes mutations, and interferes with photosynthesis in plants and phytoplankton. Phytoplankton are microscopic organisms that drift in the oceans, and they're absolutely fundamental to life on Earth. They produce roughly half of the oxygen we breathe and form the base of the marine food chain. If UV radiation disrupts their ability to photosynthesize, the entire oceanic ecosystem begins to collapse from the bottom up. On land, plants would face similar damage. Increased UV radiation would cause mutations, inhibit growth, and kill sensitive species. Animals, including humans, would experience increased rates of skin cancer, cataracts, and immune system damage. But the real killer would be the collapse of food chains as both marine and terrestrial ecosystems fail. The nitrogen oxides produced by the gamma ray burst wouldn't just destroy ozone. They would also create a brownish haze in the atmosphere, similar to smog. This haze would reduce the amount of visible sunlight reaching Earth's surface by potentially 10 to 20%. Less sunlight means cooler temperatures. The planet would experience rapid global cooling, possibly triggering widespread glaciation. There's also the matter of nitric acid rain. The nitrogen oxides would eventually combine with water vapor to form nitric acid, which would fall as acid rain. This would acidify soils and bodies of water, further stressing already damaged ecosystems. Now, here's the sobering part. Mellet and his colleagues suggest that a gamma-ray burst may have actually contributed to the late Ordovician mass extinction, approximately 440 million years ago. This extinction event killed roughly 85% of marine species and was one of the 5 major mass extinctions in Earth's history. The extinction pattern fits what we'd expect from a gamma-ray burst. There's evidence of global cooling and glaciation. Marine organisms living in shallow water, where UV radiation would penetrate, were hit particularly hard. Species that could retreat to deeper water or that had UV-resistant structures fared better. We can't prove definitively that a gamma-ray burst caused this extinction, but the evidence is compelling enough that it remains a serious hypothesis. So how worried should we be? How likely is it that Earth will be struck by a gamma-ray burst in the near future? The good news, if we can call it that, is that gamma-ray bursts are relatively rare in any given galaxy. Current estimates suggest that our Milky Way galaxy experiences a gamma-ray burst roughly once every 100,000 to 1 million years. But remember, the beam has to be pointed at us for it to affect Earth. When you account for the narrow beam width, the odds of a dangerous gamma-ray burst hitting Earth are much lower, perhaps once every few 100 million to 1 billion years. That said, we can identify certain stars in our neighborhood that could potentially produce gamma-ray bursts when they die. One of the most concerning is a star called WR104, located about 8,000 light-years away in the constellation Sagittarius. This is a Wolf-Rayet star, an extremely massive and unstable star that's near the end of its life. Wolf-Rayet stars have already shed their outer hydrogen layers, exposing their hot cores. They're burning through their remaining fuel at an extraordinary rate. WR104 is rotating rapidly, which is one of the conditions thought necessary for producing a gamma-ray burst when the star finally collapses. Observations suggest that its rotational axis might even be pointed roughly toward our solar system. However, and this is important, 8,000 light-years is probably far enough away that even if WR104 does produce a gamma-ray burst aimed at Earth, the effects would be noticeable but not catastrophic. We might see some ozone depletion and experience increased UV radiation, but it likely wouldn't cause a mass extinction. For a truly devastating gamma-ray burst, we'd need one to occur within about 3,000 light-years and have its jet pointed directly at us. The probability of this happening in any given year is extraordinarily small. But over millions of years, over the deep time scales of Earth's history, it becomes not just possible but probable that our planet has been struck by such events multiple times. This brings us to a profound realization: Earth exists in a universe that is fundamentally dangerous. Our thin atmosphere, our magnetic field, our position in a relatively quiet stellar neighborhood, these things shield us, but they don't make us invulnerable. The cosmos is filled with energetic events that could end life on our planet, and given enough time, some of them will. But gamma-ray bursts aren't the only cosmic threat we face. There's another scenario, one that unfolds more slowly but with equal finality. It involves the very structure of our galaxy and the dance of gravity on cosmic scales. Our solar system orbits the center of the Milky Way galaxy at a distance of approximately 26,000 light-years. We're moving at around 230 kilometers per second, completing one orbit roughly every 230 million years. This orbital motion isn't smooth and circular, though. It oscillates up and down through the galactic plane, and it periodically brings us closer to and farther from the galactic center. The galactic center is a crowded, violent place. It harbors Sagittarius A star, a supermassive black hole containing approximately 4 million times the mass of our Sun. Surrounding this central region are dense clusters of stars, massive molecular clouds, and regions of intense star formation. There's also significantly more radiation in this environment: cosmic rays, X-rays, and energetic particles accelerated by magnetic fields and stellar processes. Currently, our solar system resides in what astronomers call the Orion Spur, a minor spiral arm between two major arms of the galaxy. It's a relatively calm region, sparsely populated compared to the spiral arms themselves. But our galactic orbit doesn't keep us here permanently. As we orbit the galaxy, we periodically pass through the denser spiral arms. Some researchers have proposed that these passages correlate with mass extinction events in Earth's past. The hypothesis goes like this: when our solar system enters a spiral arm, we're exposed to more supernovae, more gravitational perturbations that could disrupt the Oort cloud and send comets plunging into the inner solar system, and potentially more cosmic radiation. The evidence for this correlation is debated and not conclusive. But what isn't debated is that our galactic environment changes over time, and some of those changes could be harmful to life on Earth. There's an even more dramatic galactic threat looming in our future, one that's absolutely certain to occur. Our Milky Way galaxy is on a collision course with the Andromeda galaxy, and when these two massive structures meet, the consequences will reshape our entire cosmic neighborhood. The Andromeda galaxy, also known as Messier 31, is the nearest large spiral galaxy to our own. It lies approximately 2.5 million light-years away, and here's the remarkable thing: it's heading straight toward us at roughly 110 kilometers per second. Astronomers have known about this approaching collision for decades, but it wasn't until observations from the Hubble Space Telescope in 2012 that we could measure Andromeda's sideways motion with enough precision to predict the collision's details. The research team, led by Roland van der Marel at the Space Telescope Science Institute, used careful measurements of stars in Andromeda to determine its trajectory. Their conclusion? In approximately 4 billion years, the Milky Way and Andromeda will begin their first close passage. I say first because galaxy collisions aren't quick events. They unfold over billions of years, with the two galaxies passing through each other, separating, then coming back together multiple times before finally merging into a single, larger elliptical galaxy. Now, you might imagine this collision as a catastrophic smashing together of stars, like two swarms of fireflies colliding. But the reality is both stranger and, in some ways, less immediately violent than you'd expect. Galaxies are mostly empty space. Consider this: the nearest star to our Sun is Proxima Centauri, located 4.2 light-years away. That's approximately 40 trillion kilometers. Stars are tiny compared to the vast distances between them. When two galaxies merge, the probability of any individual star actually colliding with another star is astronomically small, nearly zero. What does happen is that the gravitational fields of the two galaxies interact. Stars get flung onto new orbits. The entire structure of both galaxies gets distorted and reshaped. Computer simulations of the Milky Way-Andromeda collision, run on powerful supercomputers, show stars being scattered across vast volumes of space. Some get ejected from the merged galaxy entirely, tossed out into intergalactic space. Others get pulled toward the center. For our solar system, there are several possible outcomes. We might end up in the outskirts of the newly merged galaxy, far from the dense central regions. We could be thrown into a more elliptical orbit that periodically brings us closer to the galactic core. In extreme cases, though unlikely, our solar system could even be ejected from the galaxy entirely. But here's the critical question: what happens to Earth during all this? The good news is that the gravitational disruption, while dramatic on galactic scales, is unlikely to directly destabilize our solar system. The good news is that the gravitational disruption, while dramatic on galactic scales, is unlikely to directly destabilize our solar system. The Sun's gravitational hold on its planets is strong enough that even close passages by other stars, which might occur during the merger, would probably not tear the planets away. the solar system would likely survive the collision intact, as a coherent unit, even if its position within the galaxy changes dramatically. However, there's a complication we need to address. Remember our earlier discussion about the Sun becoming a red giant? That transformation begins in approximately 5 billion years. The Andromeda collision starts in roughly 4 billion years. These two cosmic events are happening on similar timescales. By the time the galaxies complete their merger, approximately 6 billion years from now, the Sun will already be well into its red giant phase. Earth, if it still exists, will already be a lifeless, scorched world. The galaxy collision, spectacular as it is, won't be what kills life on our planet. The Sun's own evolution will have already done that. But let's imagine for a moment a different scenario. Suppose Earth orbited a longer-lived star, one that would remain stable for 20 or 30 billion years. In that case, the galactic merger would present genuine threats to life, even if the solar system itself remained intact. During the merger, the rate of star formation would increase dramatically. When the gas clouds of the two galaxies collide, they compress and heat up, triggering waves of new star formation. These newborn stars include massive, short-lived ones that will explode as supernovae within just a few million years of forming. A supernova within 30 light-years of Earth would bathe our planet in dangerous levels of radiation, primarily cosmic rays and X-rays. This could damage the ozone layer, similar to a gamma-ray burst but potentially over a longer duration. If multiple supernovae occurred in our vicinity over a relatively short timescale, the cumulative effects could be severe enough to cause mass extinctions. Additionally, the gravitational perturbations during the merger could disturb the Oort cloud, a vast sphere of icy bodies surrounding our solar system at distances up to 100,000 astronomical units. Disrupting the Oort cloud would send showers of comets into the inner solar system, dramatically increasing the risk of impacts on Earth. But again, this is all academic for Earth specifically, because the Sun's death will occur before the worst of the galactic merger effects manifest. Yet this scenario illustrates something important: even if individual solar systems survive galaxy collisions physically intact, the changing galactic environment can pose serious threats to any life those systems harbor. The merger of the Milky Way and Andromeda is certain. It's not a matter of if, but when. And it reminds us that even structures as vast as galaxies are not permanent. They collide, merge, and evolve over cosmic time. Nothing in this universe is truly static. Speaking of things that change over cosmic time, let me tell you about a threat that operates on even longer timescales, one that involves the very fabric of space itself. Our universe is expanding. This isn't speculation or theory in the casual sense, it's one of the most well-established facts in all of cosmology. In 1929, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, and the farther away a galaxy is, the faster it's receding. This observation led to the conclusion that space itself is stretching, carrying galaxies apart like dots on an inflating balloon. For decades, astronomers assumed this expansion would gradually slow down due to the gravitational attraction of all the matter in the universe. The big question was whether there was enough matter to eventually halt the expansion and cause the universe to collapse back on itself in a big crunch, or whether the universe would expand forever, just at an ever-decreasing rate. Then came 1998, and everything changed. Two independent teams of astronomers, studying distant supernovae to measure the universe's expansion history, made a shocking discovery. The expansion of the universe isn't slowing down at all. It's accelerating. Distant galaxies are moving away from us faster and faster as time goes on. This discovery was so unexpected, so contrary to what physics predicted, that it took the astronomical community by storm. Saul Perlmutter, Brian Schmidt, and Adam Rees, leaders of the two teams, were awarded the Nobel Prize in Physics in 2011 for this work. The acceleration implies the existence of something called dark energy, a mysterious component that makes up approximately 68% of the total energy content of the universe. We don't know what dark energy is. We can observe its effects on the expansion of the universe, but its fundamental nature remains one of the biggest unsolved problems in physics. The simplest explanation for dark energy is that it's a property of space itself, a cosmological constant as Einstein once proposed. If dark energy remains constant in strength as the universe expands, then the acceleration will continue forever. The universe will expand eternally, growing ever larger, ever colder, ever more empty. What does this mean for the ultimate fate of life, not just on Earth, but anywhere in the universe? Over the next trillion years, galaxies outside our local group, the gravitationally bound collection of galaxies that includes the Milky Way, Andromeda, and several dozen smaller galaxies, will accelerate away from us. Eventually, they'll be receding faster than the speed of light. This doesn't violate relativity because it's space itself that's expanding, not the galaxies moving through space. These distant galaxies will disappear beyond our cosmic horizon. Their light will be stretched to such long wavelengths that it becomes undetectable. Any future civilization arising in our local group trillions of years from now would look out at the universe and see only the handful of galaxies in their immediate neighborhood. They would have no way to know that billions of other galaxies once existed beyond their view. Star formation will continue for a while, but it can't last forever. Stars form from clouds of gas, primarily hydrogen and helium. Each generation of stars locks some of that gas into stellar remnants, white dwarfs, neutron stars, and black holes. Over time, the supply of free gas available for making new stars dwindles. Calculations by Fred Adams and Gregory Laughlin at the University of Michigan, published in a comprehensive paper titled A Dying Universe, suggest that star formation will essentially cease in about 100 trillion years. That's 100,000 billion years, roughly 10,000 times the current age of the universe. After that, the universe enters what they call the degenerate era, dominated by stellar remnants. White dwarfs and neutron stars slowly cool, radiating away their remaining heat into the darkness of space. Brown dwarfs, failed stars that never achieved sustained fusion, drift through the void. Black holes grow slowly through occasional accretion of matter and through mergers with other black holes. This era lasts an almost incomprehensibly long time, from 10 to the 14th power years to 10 to the 40th power years. That's 1 followed by 40 zeros. To put this timescale in perspective, the current age of the universe is roughly 10 to the 10th power years. We're talking about timescales a trillion times longer than the entire history of the universe so far. During this era, there's still a slim possibility for something resembling life to exist. White dwarfs, though cooling, remain warm for an extraordinarily long time. A white dwarf could potentially have a planet in a close orbit, kept warm by the dwarf's residual heat. Life on such a planet would exist under alien conditions, a dim, cooling ember of a sun in a universe gone dark, but it's not physically impossible. However, even this faint hope eventually fades. White dwarfs cool to black dwarfs, dark and cold. And if proton decay occurs, even these remnants won't last forever. Proton decay is a theoretical process predicted by some extensions of the Standard Model of particle physics. The idea is that protons, which make up the nuclei of atoms, are not actually stable on extremely long timescales. They will eventually decay into lighter particles like positrons and photons. The current experimental lower limit on the proton half-life is about 10 to the 34th power years. If protons do decay, then after approximately 10 to the 40 power years, all the matter we're familiar with, the atoms that make up stars, planets, and our own bodies, will have disintegrated. The universe would enter what Adams and Laughlin call the black hole era, lasting from 10 to the 40 power years to 10 to the 100 power years. During this era, black holes are the only significant structures remaining. Everything else has either fallen into black holes or decayed away. But even black holes, those seemingly eternal cosmic prisons from which nothing can escape, are not truly immortal. In 1974, physicist Stephen Hawking made a remarkable discovery that fundamentally changed how we understand black holes. He showed that when you combine quantum mechanics with general relativity near the event horizon of a black hole, something extraordinary happens. Black holes emit radiation. This phenomenon, now called Hawking radiation, arises from quantum fluctuations in the vacuum of space near the event horizon. Particle-antiparticle pairs spontaneously form out of the vacuum. Normally, these pairs annihilate each other almost immediately. But near a black hole's event horizon, one particle can fall in while the other escapes. To an outside observer, it appears that the black hole is emitting radiation. Here's the crucial part: this radiation carries energy away from the black hole. Energy and mass are equivalent through Einstein's famous equation, E equals mc squared. When a black hole loses energy through Hawking radiation, it loses mass. The black hole slowly evaporates. The rate of evaporation depends on the black hole's size. Smaller black holes are hotter and evaporate faster. Larger black holes are cooler and evaporate more slowly. For a black hole with the mass of our Sun, the evaporation time is approximately 10 to the 67th power years. For a supermassive black hole containing a billion solar masses, like those found at the centers of galaxies, the evaporation time extends to 10 to the 100 power years. These timescales are so vast that they defy human comprehension. We're talking about periods trillions upon trillions of times longer than the current age of the universe. But physics doesn't care about human comprehension. Given enough time, even these timescales will pass. Eventually, the last black hole in the universe will evaporate in a final burst of radiation. And then what's left? According to our current understanding, the universe enters this dark era, an eternal expanse of dilute radiation and fundamental particles spread across an ever-expanding space. The temperature approaches absolute zero. No stars shine. No planets orbit. No complex structures exist. The universe has reached a state of maximum entropy, what physicists call heat death. This is the ultimate end of everything, not just life on Earth, but all life anywhere, all structure, all complexity, all light. The universe becomes a cold, dark, featureless void that expands forever. Now, I want to pause here and acknowledge something important. This far future scenario is based on our current best understanding of physics, particularly our understanding of dark energy. But we must remain humble about the limits of our knowledge. Dark energy was only discovered in 1998. We still don't know what it is or whether its properties might change over time. There are alternative theories to the cosmological constant. Some models propose that dark energy could strengthen over time, eventually tearing apart galaxies, stars, planets, and even atoms in what's called the Big Rip. Other models suggest dark energy could weaken or even reverse, leading to a big crunch where the universe collapses back on itself. We're also still learning about the fundamental laws of physics at the quantum level. Our current theories, quantum mechanics and general relativity, are both tremendously successful in their domains, but they're incompatible with each other at the deepest level. A complete theory of quantum gravity might reveal new physics that changes our predictions about the universe's ultimate fate. This uncertainty doesn't invalidate what we've discussed. It reminds us that science is an ongoing process of discovery. We make our best predictions based on current evidence, but we remain open to new observations and new theories. That's not a weakness of science. It's its greatest strength. Let me bring us back to timescales more relevant to Earth and to any potential future for humanity. We've talked about the Sun's death in 5 billion years and the heat death of the universe in 10 to the 100 power years. But there are scenarios that could end life on Earth much sooner, some within thousands or even hundreds of years. These scenarios are worth discussing because, unlike the distant cosmic inevitabilities, we might actually be able to do something about them. One of the most significant near-term threats is asteroid impact. Unlike the cosmic scenarios we've been exploring, asteroid impacts are not just theoretical. They've happened many times in Earth's history, and they will happen again. Approximately 66 million years ago, an asteroid roughly 10 to 15 kilometers in diameter struck the Yucatan Peninsula in what is now Mexico. The impact released energy equivalent to several billion nuclear weapons. It vaporized rock, created a crater nearly 200 kilometers across, and threw trillions of tons of debris into the atmosphere. The immediate effects were catastrophic. Earthquakes measuring magnitude 10 or higher shook the planet. Tsunamis hundreds of meters tall swept across coastlines. The heat from re-entering ejecta triggered wildfires across entire continents. But the long-term effects were even more devastating. The debris thrown into the upper atmosphere circled the globe, blocking sunlight for months to years. Surface temperatures plummeted. Photosynthesis ceased. Plants died, followed by the herbivores that depended on them, followed by the carnivores. The fossil record shows that approximately 75% of all species went extinct, including all non-avian dinosaurs. This wasn't a one-time event. The geological record shows evidence of multiple major impact events throughout Earth's history. The Chicxulub impact that killed the dinosaurs is just the most recent and most famous. There have been others, some possibly even larger. The crucial question is, could it happen again? The answer is unequivocally yes. Earth orbits the Sun within a cosmic shooting gallery. The solar system contains countless asteroids and comets, remnants from the planetary formation process for 0.6 billion years ago. Most of these objects orbit peacefully in predictable paths. But gravitational interactions can perturb their orbits, sometimes sending them on trajectories that cross Earth's path. NASA and other space agencies have been conducting surveys to identify near-Earth objects, asteroids, and comets whose orbits bring them close to our planet. The current catalog contains over 30,000 known near-Earth objects, and we discover roughly 3,000 new ones each year. The good news is that we've identified and tracked nearly all of the largest potentially hazardous asteroids, those over 1 kilometer in diameter. Current surveys estimate we've found more than 95% of objects in this size range. None of them pose a threat of impacting Earth within the next century. But here's the sobering part: there are an estimated 25,000 near-Earth asteroids larger than 140 meters that we haven't yet discovered. An object this size wouldn't cause a global extinction, but it could devastate a region the size of a country. If it struck an ocean, the resulting tsunami could kill millions. If it struck a major city, the death toll would be catastrophic. The Chelyabinsk meteor that exploded over Russia in 2013 was only about 18 meters in diameter, and we never saw it coming. The airburst released energy equivalent to roughly 400 to 500 kilotons of TNT, 30 times more powerful than the Hiroshima bomb. It damaged thousands of buildings and injured over 1,500 people, mostly from broken glass. And that was a relatively small object. Now imagine something 10 times larger. 100 times larger. The energy release scales with the cube of the diameter. A 1-kilometer asteroid impact would release energy equivalent to roughly 100,000 megatons of TNT. That's approximately 2 billion times more powerful than the Hiroshima bomb. Such an impact wouldn't necessarily kill all life on Earth. Bacteria would survive. Deep-sea ecosystems would probably persist. But human civilization, with its 7 to 8 billion people dependent on complex agricultural and technological systems, would face an existential threat. The scientific community has been taking this threat seriously. In 2022, NASA successfully conducted the Double Asteroid Redirection Test, or DART mission. A spacecraft intentionally crashed into Dimorphos, a small asteroid moon, at over 6 kilometers per second. The impact changed the asteroid's orbital period by 33 minutes, demonstrating that we have the technology to deflect a threatening asteroid if we detect it early enough. This is crucial. Early detection is everything. With decades of warning, we could launch multiple spacecraft to gradually nudge a threatening asteroid onto a safe trajectory. With only months or years of warning, our options become much more limited and risky. This brings us to an important philosophical point about existential risks. Some threats, like the sun becoming a red giant, are inevitable and operate on timescales so long that they're not immediate concerns for our species. Other threats, like asteroid impacts, are probabilistic. They might happen tomorrow, or not for millions of years, but we can take concrete steps to reduce the risk. The challenge is balancing our limited resources between addressing immediate problems and preparing for unlikely but catastrophic future scenarios. It's a question that doesn't have easy answers, but it's one we must grapple with as a civilization. There's another near-term existential threat worth discussing, one that comes not from space but from Earth itself. I'm talking about supervolcanic eruptions. Beneath Yellowstone National Park in Wyoming lies one of the largest volcanic systems on Earth. It's not a mountain-shaped volcano like Mount St. Helens or Mount Fuji. Instead, it's a vast caldera, a collapsed volcanic depression measuring roughly 70 kilometers across. Beneath this caldera sits a massive chamber of molten rock, a magma reservoir that extends down into the Earth's mantle. Yellowstone is what geologists call a supervolcano. These are volcanic systems capable of eruptions at least 1,000 times more powerful than ordinary volcanic eruptions. When a supervolcano explodes, it doesn't just affect the immediate area. It has global consequences. Yellowstone has erupted 3 times in the past 2.1 million years. The first eruption, 2.1 million years ago, ejected approximately 2,400 cubic kilometers of material. The second, 1.3 million years ago, ejected 280 cubic kilometers. The most recent, 640,000 years ago, ejected 1,000 cubic kilometers of ash, rock, and lava. To put this in perspective, the 1980 eruption of Mount St. Helens ejected approximately 1 cubic kilometer of material. The 1883 eruption of Krakatoa, one of the most powerful eruptions in recorded history, ejected roughly 25 cubic kilometers. Yellowstone's last eruption was 40 times more powerful than Krakatoa, and its first eruption was nearly 100 times more powerful. When a supervolcano erupts, the magma chamber empties so rapidly that the ground above it collapses, forming a caldera. Pyroclastic flows, superheated clouds of gas and rock fragments traveling at hundreds of kilometers per hour, race across the landscape, incinerating everything in their path. These flows can extend for hundreds of kilometers from the source. But the regional devastation, as terrible as it would be, isn't the real global threat. The real danger comes from the ash. Volcanic ash isn't like the soft, fluffy ash from a campfire. It's made of tiny fragments of rock and glass, sharp and abrasive. When a supervolcano erupts, it throws billions of tons of this material high into the stratosphere, where it spreads across the planet. Computer models of a major Yellowstone eruption suggest that ash deposits several meters thick would blanket much of the western United States. Ash would contaminate water supplies, collapse buildings under its weight, destroy crops, and create massive respiratory health problems. Air travel across North America would cease entirely. Jet engines cannot function when ingesting volcanic ash. But the effects would extend far beyond North America. The ash in the stratosphere would reflect sunlight back into space, cooling the planet. This phenomenon is well documented from smaller eruptions. The 1815 eruption of Mount Tambora in Indonesia ejected approximately 160 cubic kilometers of material and caused the year without a summer in 1816. Temperatures across the northern hemisphere dropped by approximately 0.4 to 0.7 degrees Celsius. Crops failed across Europe and North America. Food prices soared. Widespread famine resulted. Now scale that up by a factor of 10 or more. A major Yellowstone eruption could drop global temperatures by several degrees Celsius for years. Growing seasons would shorten dramatically. Agricultural production would collapse. With our current global population of 8 billion people, the majority dependent on modern agriculture, the death toll from famine could reach into the hundreds of millions or even billions. Would it end all life on Earth? No. Would it end human civilization as we know it? Quite possibly. The question everyone asks is, when will Yellowstone erupt next? The honest answer is that we don't know. The three major eruptions occurred approximately 660,000 years apart, and it's now been 640,000 years since the last one. This has led to sensationalist claims that Yellowstone is overdue for an eruption. But volcanic systems don't operate on strict schedules. The intervals between past eruptions varied considerably, and there's no guarantee that another major eruption will occur anytime soon, if ever. The United States Geological Survey maintains an extensive monitoring network at Yellowstone, tracking earthquakes, ground deformation, and gas emissions. These measurements help scientists understand what's happening beneath the surface. The current assessment is that while Yellowstone remains an active volcanic system, there are no signs of an imminent major eruption. In fact, the most likely volcanic event in the near future would be a much smaller lava flow, not a catastrophic explosive eruption. But Yellowstone isn't the only supervolcano on Earth. The Toba supervolcano in Indonesia erupted approximately 74,000 years ago in one of the largest volcanic events of the past 2 million years. It ejected an estimated 2,800 cubic kilometers of material, even more than Yellowstone's largest eruption. Some researchers have proposed that the Toba eruption caused a volcanic winter that lasted 6 to 10 years, followed by a cooling period that lasted 1,000 years. There's even a controversial hypothesis that this eruption created a population bottleneck in human evolution, reducing our species to perhaps 10,000 or fewer individuals. The evidence for this bottleneck is debated. Genetic studies do suggest that human genetic diversity is relatively low compared to other species, consistent with a severe population reduction in our past. But whether Toba was the cause, and whether the bottleneck was as severe as some researchers suggest, remains uncertain. What's not uncertain is that supervolcanic eruptions have occurred repeatedly in Earth's past and will occur again in the future. The question isn't if, but when, and whether human civilization will be ready when it happens. Unlike asteroid deflection, we have no technology to prevent a supervolcanic eruption. The energies involved are simply too vast. The best we can do is monitor these systems, try to predict when eruptions might occur, and prepare for the consequences. This means maintaining strategic food reserves, developing crop varieties that can grow in cooler conditions with reduced sunlight, and building resilient systems that can maintain social order during prolonged crises. Now let me take you to another threat, one that's perhaps even more insidious because it operates on such a gradual timescale that we might not recognize the danger until it's too late. Earth's climate has changed dramatically throughout our planet's history. There have been periods when the entire planet was covered in ice, events called snowball Earth episodes. The most recent of these occurred approximately 700 million years ago. Geological evidence suggests that ice extended from the poles all the way to the equator. The oceans froze over. Life persisted, but only in isolated refuges. There have also been periods much warmer than today. During the Paleocene thermal maximum, approximately 56 million years ago, global temperatures were roughly 8 degrees Celsius warmer than today. The Arctic was ice-free and supported crocodiles and palm trees. Ocean chemistry changed dramatically, causing major extinctions in marine life. These climate changes were driven by various factors: changes in Earth's orbit and axial tilt, volcanic activity releasing greenhouse gases, the arrangement of continents affecting ocean currents, even the evolution of photosynthetic organisms removing carbon dioxide from the atmosphere. The point is that Earth's climate is not static. It changes, sometimes gradually over millions of years, sometimes quite rapidly over thousands or even hundreds of years. And these changes have profound effects on life. Now, here's where we must address the elephant in the room: human-caused climate change. I want to be absolutely clear about something. The scientific evidence that Earth's climate is warming due to human greenhouse gas emissions is overwhelming. It's supported by multiple independent lines of evidence: direct temperature measurements, satellite observations, ocean heat content, ice core data, and the basic physics of how greenhouse gases interact with infrared radiation. The question for this discussion isn't whether human-caused climate change is real, it is. The question is whether it represents an existential threat to life on Earth, or specifically to human civilization. Climate change will not make Earth uninhabitable in the way that the Sun becoming a red giant will. It will not sterilize the planet. Life has persisted through far more dramatic climate changes than what we're currently experiencing or are likely to experience in the next few centuries. The planet itself will be fine. But the planet will be fine is cold comfort when we're talking about human welfare. We're not asking whether bacteria or cockroaches will survive. We're asking whether our civilization, our cities, our agricultural systems, our way of life can survive. The projections depend heavily on how much greenhouse gas we emit over the coming decades. If we continue with business as usual, with high emissions, models project global temperature increases of 3 to 5 degrees Celsius by 2100, with further warming beyond that if emissions continue. This might not sound like much. After all, temperatures can vary by more than that from day to night, or between seasons. But we're talking about global average temperatures. A few degrees change in global average has enormous implications. During the last ice age, when ice sheets covered much of North America and Europe, global average temperatures were only about 4 to 7 degrees Celsius colder than today. That difference put Chicago under a kilometer of ice. It lowered sea levels by 120 meters, exposing land bridges between continents. It completely reorganized global ecosystems. Now imagine the same magnitude of change, but in the opposite direction, and happening much faster than the natural transitions between ice ages and warm periods. Sea level rise is one of the most certain consequences. Water expands when it warms, that's basic physics. Additionally, land-based ice sheets in Greenland and Antarctica are melting and adding water to the oceans. Current projections suggest sea level rise of 0.5 meter to 1 meter by 2100 under moderate emission scenarios, with higher rises under high emission scenarios. That might not sound catastrophic, but consider this: hundreds of millions of people live in coastal areas less than 10 meters above sea level. Major cities like Miami, Shanghai, Mumbai, Lagos, and Bangkok face serious flooding risks. Even a 1-meter rise would inundate vast areas of low-lying countries like Bangladesh, displacing tens of millions of people. And sea level won't stop rising in 2100. Once set in motion, ice sheet melting continues for centuries. Paleoclimate evidence from periods when temperatures were 2 to 3 degrees warmer than today shows sea levels were 6 to 9 meters higher. If we commit to that level of warming, we commit to eventually losing most coastal cities, even if the full impact takes centuries to manifest. Heat waves become more frequent and more severe in a warmer world. This isn't speculation, we're already seeing it. The human body has limits to how much heat it can tolerate. When both temperature and humidity are high, the body cannot cool itself through sweating. Prolonged exposure to these conditions is fatal. Currently, such deadly combinations of heat and humidity are rare and short-lived. But climate models project that under high warming scenarios, regions of South Asia, the Middle East, and potentially parts of Central and South America could experience regular periods where outdoor work becomes impossible and even staying inside without air conditioning becomes life-threatening. This creates a grim scenario. The regions most vulnerable to extreme heat tend to be poorer regions with less access to air conditioning and less infrastructure to protect people. Climate change, in this sense, is deeply unjust. Those who contributed least to the problem often face the worst consequences. Agriculture faces major disruptions. Crop yields are sensitive to temperature, rainfall patterns, and extreme weather events. While some northern regions might see improved growing conditions, many current agricultural areas, particularly in tropical and subtropical regions, will likely see reduced productivity. When you're trying to feed 8 billion people, or 10 billion as projected for later this century, declining agricultural productivity in major breadbasket regions is a serious concern. There's also the question of feedback loops and tipping points. Earth's climate system is complex, with many interconnected components. Some of these components could undergo sudden, non-linear changes once certain thresholds are crossed. For example, the Amazon rainforest creates much of its own rainfall through evapotranspiration, water evaporating from leaves and soil. If deforestation and climate change reduce rainfall below a critical threshold, the forest could undergo a rapid transition to savanna. This would release enormous amounts of carbon currently stored in trees, accelerating warming further. Arctic permafrost contains vast amounts of frozen organic matter. As temperatures rise and permafrost thaws, microbes decompose this organic matter, releasing carbon dioxide and methane, both greenhouse gases. This releases more carbon, causing more warming, thawing more permafrost, another feedback loop. The Atlantic meridional overturning circulation, which includes the Gulf Stream, transports heat from the tropics toward the North Atlantic. This ocean current is driven partly by differences in water density. As Arctic ice melts and fresh water flows into the North Atlantic, it could weaken this circulation. Some models suggest it could slow significantly or even shut down this century, which would paradoxically cause regional cooling in Europe even as the planet as a whole warms. These are complex systems, and predicting exactly when or if these tipping points might be crossed is difficult. But the possibility that we could trigger rapid, self-reinforcing changes is precisely why many scientists are deeply concerned about climate change. Now, let me be clear about what climate change is unlikely to do. It is very unlikely to cause human extinction in the next few centuries. Humans are remarkably adaptable. We live in environments from the Arctic to the Sahara Desert. We have technology that allows us to control our local environment to a degree unprecedented in any other species. But there's a vast difference between humans will survive somewhere and civilization will continue functioning as it does today. Climate change threatens not extinction, but massive disruption, displacement of hundreds of millions of people, failures of agricultural systems, collapse of ecosystems we depend on, conflicts over increasingly scarce resources like water and arable land. The worst-case scenarios involve not climate change alone, but climate change interacting with other stressors, resource depletion, political instability, potential pandemics, technological risks. It's the combination that poses the greatest danger to civilizational stability. Which brings me to another category of existential risk, one that's entirely of our own making, the risk from advanced technology. We live in an era of unprecedented technological power. Technologies that would have seemed like magic to people just a few generations ago are now commonplace. This trend is accelerating. And with increased power comes increased risk. Nuclear weapons represent the most obvious technological existential risk. Since 1945, humanity has possessed the ability to destroy civilization. At the peak of the Cold War, the United States and Soviet Union possessed roughly 70,000 nuclear warheads between them. Current stockpiles are smaller, around 13,000 warheads total across all nuclear powers, but that's still more than enough to devastate human civilization. A large-scale nuclear war would kill hundreds of millions of people directly through blast effects, radiation, and fires. But the indirect effects could be even worse. In the 1980s, scientists studying the potential consequences of nuclear war developed the concept of nuclear winter. The idea is this: nuclear explosions over cities would ignite massive firestorms. These fires would inject enormous amounts of smoke and soot into the stratosphere. This smoke would spread globally and persist for years, blocking sunlight much like the ash from a supervolcanic eruption. Temperatures would drop. Photosynthesis would be reduced. Agricultural production would collapse. Early models suggested temperature drops of 20 to 30 degrees Celsius, essentially triggering an ice age. More recent models with improved climate simulations suggest somewhat smaller temperature drops, perhaps 5 to 15 degrees Celsius depending on the scale of the war. But even the lower end of this range would be catastrophic for global agriculture. The term nuclear winter became well known during the Cold War and contributed to public awareness of just how dangerous nuclear weapons are, not just to the nations involved in a conflict but to the entire planet. Carl Sagan was particularly effective at communicating this risk to the public. The Cold War ended, and the immediate fear of nuclear war diminished. But the weapons remain. The United States and Russia still maintain large arsenals on high alert status, capable of being launched within minutes. Other nations have developed nuclear weapons: United Kingdom, France, China, India, Pakistan, Israel, and North Korea. The risk today isn't the same as during the Cold War. A deliberate, all-out nuclear exchange between superpowers seems less likely. But new risks have emerged: nuclear terrorism, accidental launch due to false alarms or cyber attacks, regional nuclear war between newer nuclear powers, proliferation to unstable states. Even a relatively small nuclear war could have global consequences. A war between India and Pakistan, involving perhaps 100 Hiroshima-sized weapons, could inject enough smoke into the stratosphere to cause global cooling and food shortages affecting billions of people. This isn't speculation, it's based on detailed climate modeling by researchers at Rutgers University and other institutions. The fundamental problem is that nuclear weapons exist and we cannot invent them. The knowledge of how to build them is permanently part of human understanding. Even if we somehow eliminated every nuclear weapon on Earth, they could be rebuilt. The genie cannot be put back in the bottle. This is true of many technologies. Once we develop the knowledge and capability to do something, that capability persists. And as technology advances, capabilities that once required nation-states become accessible to smaller groups or even individuals. Consider biotechnology. Our ability to manipulate living organisms at the genetic level has advanced enormously over the past few decades. CRISPR gene editing, developed in the early 2010s, has made genetic modification dramatically easier, cheaper, and more precise. What once required specialized laboratories and millions of dollars can now be done by graduate students with equipment costing thousands of dollars. This technology has enormous potential benefits. We can develop crops that are more nutritious, more resistant to pests and drought, and that grow in marginal soils. We can potentially cure genetic diseases by editing faulty genes. We might be able to bring back extinct species or save endangered ones. The possibilities are genuinely exciting. But the same technology that can cure diseases can also create them. Natural pandemics have killed enormous numbers of people throughout history. The Black Death in the 14th century killed roughly 1/3 of Europe's population. The 1918 influenza pandemic killed an estimated 50 million people worldwide, about 3% of the global population at the time. COVID-19, despite modern medicine and public health measures, killed millions. These were all natural pathogens, evolved through natural selection without any intention of maximizing harm to humans. Now imagine what might be possible with deliberately designed pathogens. A pathogen optimized for transmissibility, with a long incubation period during which infected individuals show no symptoms but can spread the disease, with a high fatality rate once symptoms appear, and with resistance to known treatments, could theoretically spread globally before we even knew we were facing a pandemic. By the time we recognized the threat and began developing countermeasures, billions could already be infected. The 2001 publication of the complete genome of the smallpox virus raised concerns about this exact scenario. Smallpox was eradicated in the wild in 1980, one of humanity's greatest public health achievements. But the virus exists in frozen samples in laboratories in the United States and Russia. And now its complete genetic sequence is publicly available. Could someone synthesize smallpox from scratch using that sequence and modern biotechnology? Possibly, though it would still require significant expertise and resources. More concerning is the possibility of creating something worse than smallpox. Researchers studying pathogen evolution have, on several occasions, created more dangerous versions of viruses in laboratory settings. In 2011, researchers created a version of H5N1 avian influenza that could transmit efficiently between mammals, something the wild virus could not do. Their goal was to understand how such mutations could arise naturally so we could better prepare. But the research was highly controversial because it also created a blueprint for creating a pandemic pathogen. This is the dual-use dilemma in biotechnology. Research intended to defend against biological threats inherently involves studying how to create those threats. The knowledge cannot be neatly separated into good applications and bad applications. And unlike nuclear weapons, which require rare materials and sophisticated engineering, biotechnology is becoming increasingly accessible. The equipment needed for genetic engineering is becoming cheaper and more widespread. The knowledge is published in scientific journals and taught in universities. DIY biology communities allow hobbyists to conduct genetic engineering experiments in their homes or community laboratories. Most people in these communities have entirely benign intentions. They are hobbyists fascinated by biology or entrepreneurs hoping to develop useful products. But it only takes one person with malicious intent, or even one person making a terrible mistake, to potentially unleash a catastrophe. The scientific community has been grappling with how to manage these risks. There are biosafety regulations, institutional review boards, and international agreements like the Biological Weapons Convention. But enforcement is difficult, especially as the technology becomes more decentralized. Some researchers have proposed that certain types of gain-of-function research that makes pathogens more dangerous, should be restricted or banned entirely. Others argue that such research is necessary to stay ahead of naturally evolving pathogens and that restricting it would leave us more vulnerable, not less. There's no easy answer. We are facing a fundamental challenge. As our technological capabilities increase, so does our power to do both tremendous good and tremendous harm. And the same tools enable both. This brings us to perhaps the most discussed technological risk in recent years: artificial intelligence. The systems we call artificial intelligence today are, for the most part, narrow AI systems that can perform specific tasks, sometimes better than humans, but without general intelligence or consciousness. Your smartphone's voice assistant, recommendation algorithms on streaming services, the systems that analyze medical images or drive cars, these are all narrow AI. But many researchers believe that artificial general intelligence, or AGI, systems with human-level intelligence across a broad range of tasks, is possible and potentially could be developed within this century. Some predictions put it within the next few decades, though there's enormous uncertainty about these timelines. And if AGI is possible, then artificial superintelligence, systems vastly more intelligent than humans, is likely also possible. After all, there's no reason to think that the human brain represents the upper limit of possible intelligence. The concern, articulated by researchers like Nick Bostrom and Stuart Russell, is that superintelligent AI might pose an existential risk to humanity. Not because it would necessarily be malicious, but because its goals might not be aligned with human values and welfare. Imagine an AI system tasked with maximizing paperclip production. It's a deliberately silly example, but it illustrates a serious point. If the system is sufficiently intelligent and given enough autonomy, it might convert more and more resources into paperclip manufacturing. It might resist attempts to turn it off because being turned off would prevent it from making more paperclips. Taken to an extreme, it might convert all available matter, including matter that makes up humans and the biosphere, into paperclips or paperclip manufacturing infrastructure. This is the alignment problem. How do we ensure that advanced AI systems pursue goals that are compatible with human flourishing? It turns out to be remarkably difficult. You might think, just program it to do what we want. But what do we want? Human values are complex, often contradictory, and difficult to specify precisely. They vary across cultures and change over time. How do you encode "be helpful but don't do anything harmful" in a way that a superintelligent system couldn't find dangerous loopholes in? You might think, just keep it contained, don't give it access to the internet or to actuators that could affect the physical world. But a superintelligent system might be very good at manipulation. It could potentially convince or trick its human operators into giving it more access. Or it could discover exploits in its containment we haven't thought of. You might think, we'll just turn it off if it starts doing something we don't like. But if the system is intelligent enough to anticipate this possibility, it has an incentive to prevent being turned off, because being turned off would prevent it from achieving whatever goals it has. It might act deceptively, appearing aligned until it's in a position where it can't be stopped. These aren't just theoretical concerns. We already see simplified versions of these problems with current AI systems. Recommendation algorithms optimized for engagement can promote increasingly extreme content because that's what keeps people clicking. AI systems trained on biased data can perpetuate or amplify those biases. These are manageable problems with current, narrow AI. But they hint at the difficulties we'll face with more advanced systems. The counter-argument is that these concerns are overblown, that we'll develop safeguards as the technology advances, and that the benefits of AI will vastly outweigh the risks. And it's true that AI has enormous potential to solve problems, accelerating scientific research, developing new medicines, optimizing resource use, personalizing education, and countless other applications. But I want to emphasize something important: the concern about AI risk isn't that AI will inevitably destroy us. It's that it could, if we're not very careful about how we develop it. It's a risk that requires serious thought and research now, before we develop systems so advanced that we can't control them. The good news is that many AI researchers are taking this seriously. There's an entire field dedicated to AI safety and alignment research. Major AI laboratories have teams working on these problems. But it's unclear whether this work is progressing fast enough relative to the advancement of AI capabilities. There's also a concerning dynamic at play. AI development is economically valuable and strategically important. Countries and companies are racing to develop more advanced AI. This competitive pressure might incentivize cutting corners on safety, deploying systems before they're fully understood, or keeping research secret rather than sharing safety insights with the broader community. This is similar to the dynamics during the early development of nuclear weapons. The strategic importance of the technology drove rapid development without full understanding of the consequences. The difference is that nuclear weapons require rare materials and massive industrial infrastructure. AI requires computers and electricity, both of which are becoming more abundant and more widely distributed. Let me step back from specific risks and talk about something more fundamental: the nature of existential risk in an era of advanced technology. Throughout most of human history, the greatest threats to human survival came from nature: predators, disease, starvation, natural disasters. Our ancestors developed agriculture, built shelters, created medicines, and organized societies partly to protect against these natural threats. And we've been remarkably successful. Most people today live longer, healthier, more comfortable lives than at any previous point in human history. But in the process of protecting ourselves from natural risks, we've created new, artificial risks. And these artificial risks have a fundamentally different character. Natural risks tend to be localized or self-limiting. A plague might devastate a region, but some populations would survive due to geographic isolation or natural immunity. A volcanic eruption might cause temporary climate disruption, but the effects diminish over time. Even asteroid impacts, while devastating, have happened repeatedly in Earth's history without sterilizing the planet. But some technological risks are global and potentially permanent. A nuclear war affects the entire planet simultaneously. A pandemic engineered for maximum transmissibility could spread globally before containment is possible. A misaligned superintelligent AI could potentially affect all of humanity at once. We're also facing what some researchers call the vulnerable world hypothesis, proposed by philosopher Nick Bostrom. The idea is that scientific and technological advancement might eventually discover what Bostrom calls a black ball, a technology that makes it easy for individuals or small groups to cause catastrophic harm. Throughout history, we've drawn many discoveries from the urn of possible technologies. Most are white balls, technologies that are beneficial or at worst cause limited harm. Some are gray balls, technologies that are dangerous but can be managed through regulation, security, or international cooperation. Nuclear weapons might be a gray ball. They're dangerous, but they require rare materials and sophisticated engineering, making them difficult to acquire and relatively easy to monitor. But what if there exist black balls, technologies that are both extremely dangerous and impossible to effectively restrict? Imagine a technology as destructive as nuclear weapons but as easy to create as baking a cake. Once discovered, such a technology might make civilizational collapse inevitable. We don't know if such technologies exist, but we can't rule out the possibility. And every scientific advance brings us more discoveries from the urn. The question is whether we'll develop the wisdom and governance structures to handle these discoveries before we encounter a black ball. This brings us to a crucial realization: the greatest existential risk we face might not be any specific technology or threat, but our collective inability to coordinate globally to manage these risks. Climate change requires global cooperation to reduce emissions. Asteroid deflection requires sharing information and coordinating space missions. Managing biotechnology risks requires international agreements on research standards and enforcement. AI safety requires cooperation between researchers, companies, and governments across national boundaries. Nuclear risk reduction requires trust and verification between potentially adversarial nations. Yet our global governance institutions remain weak. The United Nations can pass resolutions but has limited enforcement power. International treaties depend on voluntary compliance. National interests often override collective welfare. Misinformation and polarization make it difficult to build consensus even on basic facts. We're like passengers on a ship headed toward an iceberg, arguing about who should steer while the ship continues on its current course. This isn't to say that cooperation is impossible. We have examples of successful international coordination: the Montreal Protocol that phased out ozone-depleting substances, the international cooperation that led to the eradication of smallpox, the treaties limiting nuclear testing and proliferation. But the challenges we face now and in the coming decades may be more difficult than anything we've collectively managed before. They require not just cooperation but sustained cooperation over long time periods. They require making sacrifices now to prevent harms that might not manifest for decades or generations. They require coordinating across different cultures, political systems, and economic interests. Human psychology isn't particularly well suited to these challenges. We evolved to respond to immediate, visible threats: the predator in the bushes, the hostile neighboring tribe. We're less good at responding to abstract, distant, or probabilistic threats. A 10% chance of catastrophe in 50 years doesn't activate our threat response systems the way a snarling animal does. This is why climate change, despite overwhelming scientific evidence, has been so difficult to address politically. The harms are mostly in the future. They're distributed globally rather than concentrated locally. The connection between cause and effect, burning fossil fuels today leading to climate impacts decades later, isn't immediately visible. The same psychological challenges apply to other long-term risks. It's hard to maintain vigilance against threats that might not manifest for years or decades. It's hard to invest resources in prevention when those resources could be used to address immediate problems. And yet, we must find ways to overcome these psychological limitations. Because the risks are real, even if they don't trigger our evolved threat responses. Let me now address a question that might be forming in your mind. Given all these risks, are we doomed? Is human extinction or civilizational collapse inevitable? The answer is no. None of these outcomes are inevitable. Every risk I've discussed has potential solutions or mitigation strategies. We can detect and deflect asteroids. We can monitor supervolcanoes and prepare for eruptions. We can reduce greenhouse gas emissions and adapt to unavoidable climate changes. We can improve biosafety and biosecurity measures. We can develop AI alignment techniques and governance frameworks. We can strengthen nuclear non-proliferation and reduce arsenals. The question isn't whether solutions exist. It's whether we'll implement them in time and with sufficient commitment. And this is where I want to inject a note of cautious optimism. Humans are remarkably good at solving problems when we focus our attention and resources on them. The response to COVID-19, despite all its flaws and failures, demonstrated this. We developed multiple effective vaccines in less than a year, a feat that would have seemed impossible a decade earlier. We created global surveillance networks to track viral variants. We developed new therapeutic treatments. When motivated, humans can accomplish extraordinary things. The challenge is maintaining that focus and motivation for threats that haven't yet materialized, for risks that are probabilistic rather than certain, for problems that require sustained effort over decades rather than months. There's also reason to think that some risks might be self-limiting through anthropic selection effects. Consider biotechnology. Yes, it's possible that someone could engineer a pathogen that kills everyone. But it's less clear that anyone would actually want to do this. Even the most misanthropic terrorist generally has some group they identify with and want to preserve. A pathogen engineered to be indiscriminately lethal kills the creator and everyone they care about along with everyone else. This doesn't mean bioterrorism isn't a serious risk, it is. But it does suggest that truly omnicidal threats, ones designed to kill literally everyone, might be less likely than threats designed to kill many people but not all people. And if some people survive, civilization might be severely damaged but not ended. Similarly, with AI risk, there's debate about whether a superintelligent AI would actually have goals that conflict with human survival. Some researchers argue that sufficiently intelligent systems might converge on values that recognize the importance of preserving diverse forms of intelligence and consciousness, including humans. Others argue that we shouldn't count on this and need to actively ensure alignment. These debates are ongoing, and I don't want to suggest that the risks are negligible. But uncertainty cuts both ways. Just as things could be worse than we expect, they could also be better. There's also the possibility of positive feedback loops, not just negative ones. As we develop more advanced technology, we also develop better tools for managing the risks that technology creates. Better surveillance systems for detecting pandemics. Better climate modeling for predicting and preparing for changes. Better space technology for planetary defense. Better AI systems for helping us solve alignment problems. The race is between our growing power and our growing wisdom. The outcome isn't predetermined. Now let me address the very long-term future, beyond the next few centuries, assuming humanity does successfully navigate the near-term risks we've discussed. On timescales of millions or billions of years, the risks change character. The threats aren't primarily from human actions or even from random astronomical events, but from the inevitable evolution of the Sun and the universe itself. Our Sun is currently about 4.6 billion years old, roughly halfway through its main sequence lifetime. For the next few billion years, it will continue fusing hydrogen into helium in its core, gradually becoming brighter and hotter as it ages. This gradual brightening has profound implications for Earth's habitability. Climate models suggest that in approximately 500 million to 1 billion years, the Sun will be bright enough that Earth's oceans will begin to evaporate. Water vapor is a greenhouse gas, so this creates a runaway feedback loop. More water vapor leads to more warming, which evaporates more water, which leads to more warming. Eventually, Earth's surface temperature will rise beyond the boiling point of water. The oceans will boil away. The water vapor will be broken down by ultraviolet radiation in the upper atmosphere, and the hydrogen will escape to space. Earth will become something like Venus is today, a scorched, desiccated world with surface temperatures hot enough to melt lead. This is a billion years in the future, give or take a few 100 million years. It's hard to comprehend such timescales. A billion years ago, life on Earth consisted primarily of single-celled organisms. The first multicellular animals had just begun to appear. Everything we think of as the history of complex life, fish, dinosaurs, mammals, humans, all of civilization, has happened in less than 1 billion years. So a billion years is an almost incomprehensibly long time for a species or civilization to persist. Perhaps by then, if humanity or our descendants still exist, we'll have spread to other star systems, making Earth's fate less critical to our survival. But even if we remain on Earth, we might develop technology to manage this risk. We could potentially alter Earth's orbit, moving it gradually outward as the sun brightens, maintaining the conditions necessary for life. Or we could engineer massive sunshades in space to reflect excess solar radiation. Or we could develop enclosed habitats independent of Earth's natural environment. These sound like science fiction, but on billion-year timescales, they're not unreasonable. If human technological progress continues, even at a much slower rate than today, our capabilities a million years from now, much less a billion years, would be literally incomprehensible to us today. Assuming Earth's eventual fate doesn't end humanity, we face an even longer-term challenge, the death of the Sun itself. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core. When this happens, the core will contract and heat up, while the outer layers expand dramatically. The Sun will become a red giant, expanding to perhaps 100 times its current radius. This will likely engulf Mercury and Venus, and possibly Earth as well. Even if Earth's orbit isn't directly engulfed, the planet will be subjected to intense heat and stellar wind that will strip away the atmosphere and boil away any remaining material. There's no plausible scenario where Earth remains habitable through this phase. The Sun will spend about 1 billion years as a red giant, fusing helium in its core and going through various stages of expansion and contraction. Eventually, it will shed its outer layers in a planetary nebula, leaving behind a white dwarf, the dense, slowly cooling core of the star. This white dwarf will initially be very hot but will gradually cool over billions of years, eventually becoming a cold, dark cinder. At this point, the solar system as we know it will essentially be dead. No warmth, no light, just frozen planets orbiting a stellar remnant. But again, this is billions of years in the future. If humanity still exists in any form, we will almost certainly not be confined to this single solar system. There are hundreds of billions of stars in our galaxy, many of them with planets. Some of these planets are likely habitable for life as we know it. The challenge is getting there. The distances between stars are vast. The nearest star system to us, Alpha Centauri, is about 4.4 light-years away. With current spacecraft technology, it would take tens of thousands of years to reach. We would need fundamentally new propulsion technologies, perhaps fusion drives, antimatter engines, or even more exotic possibilities, to make interstellar travel practical. But again, on timescales of billions of years, developing such technologies doesn't seem impossible. The bigger question might be whether biological humans, as we exist today, will be the ones spreading to the stars, or whether it will be our distant descendants, perhaps radically transformed through genetic engineering, cybernetic enhancement, or even transcendence into entirely new forms of existence we can barely imagine. This brings up profound philosophical questions about continuity and identity. If our descendants a billion years from now are so transformed that they share almost nothing with us except perhaps a historical lineage, are we still saving humanity by ensuring their existence? Or are they something else entirely? I don't have answers to these questions. I'm not sure anyone does. But they're worth contemplating when we think about very long-term existential risks. Even if humanity or our descendants spread across the galaxy, we eventually face cosmological scale challenges. The universe itself is expanding, and that expansion is accelerating due to what physicists call dark energy. Galaxies are moving apart from each other at increasing speeds. Eventually, galaxies outside our local group will be moving away from us faster than light can travel, making them forever unreachable. This process takes tens of billions of years, but eventually, the night sky will darken as distant galaxies disappear beyond the cosmic horizon. If human descendants exist at this time, they'll be confined to whatever portion of the universe they've managed to reach before this cosmic isolation sets in. Stars will continue to form and die, but the supply of raw material for star formation is finite. Current estimates suggest that star formation will peak soon, in cosmic terms, and then gradually decline. In perhaps 1 trillion years, the last stars will form. After that, as existing stars die, the universe will gradually darken. In 10 trillion to 100 trillion years, all the stars will have burned out. The universe will be populated primarily by stellar remnants, white dwarfs, neutron stars, and black holes, along with planets and various forms of dark matter and gas. White dwarfs will slowly cool and crystallize, becoming black dwarfs, cold, dark, crystalline spheres. This process takes longer than the current age of the universe, so no black dwarfs exist yet. But given enough time, trillions upon trillions of years, this is the fate of most stellar mass. At these timescales, even seemingly stable structures decay. Planets are gradually ejected from their orbits around stellar remnants through gravitational interactions. Black holes slowly evaporate through Hawking radiation, though this process takes an incomprehensibly long time. Eventually, the universe approaches what's called heat death. All structures have decayed, all temperature differences have equalized, and the universe reaches maximum entropy. No further change is possible. It's the ultimate end, not with a bang but with a whimper, a cold, dark, eternally unchanging state. These timescales are so vast that they're essentially meaningless in any human context. The entire history of the universe so far, 13.8 billion years, is infinitesimally small compared to these timescales. The idea that consciousness or civilization could persist for such duration seems absurd. And yet, we can imagine it. We can conceive of intelligence that's not tied to biological forms, that operates on vastly different timescales, that finds ways to extract energy from even the dying universe. Perhaps consciousness could encode itself in the quantum fluctuations of decaying matter, or in the structure of space-time itself, persisting in forms we cannot currently comprehend. Or perhaps not. Perhaps consciousness and complexity are inevitably temporary, brief bright moments in the long cosmic darkness. Perhaps the universe will eventually be empty, cold, and dead, with no awareness remaining to witness it. These are the ultimate existential questions, operating on scales where the distinction between existence and non-existence becomes almost philosophical. But let me bring us back to a more human scale, because I think focusing too much on these cosmological timescales can actually be paralyzing and distract from more immediate concerns. The heat death of the universe is not something we need to worry about today. Or in 1,000 years. Or even in 1 billion years. It's so far beyond any practical concern that treating it as a risk to manage is somewhat absurd. The risks that matter, the ones that should shape our decisions and priorities, are the ones we might actually face: the asteroid that could hit in a century, the climate changes unfolding over decades, the pandemic that could emerge next year, the AI systems we might develop in the coming decades. Let me now shift our discussion to something I've touched on but want to explore more deeply: the relationship between existential risk and human values, and why preventing extinction matters. This might seem like an odd question. Isn't it obvious that human extinction would be bad? But when you think carefully about it, the question of why extinction is bad, and for whom, becomes philosophically complex. If humans go extinct, there are no humans left to experience the loss. The dead don't suffer from being dead, they simply don't exist to experience anything. So in what sense is extinction bad? One answer is that it's bad for all the people who die in the process of extinction. If humanity goes extinct through nuclear war or pandemic, billions of people will suffer and die, and that suffering is clearly bad. But suppose humanity went extinct peacefully, perhaps everyone simply chose not to have children, and the population gradually declined to zero over a few generations. Would that be bad? Some philosophers argue yes, because of what's lost, all the potential future people who could have existed, all the experiences they could have had, all the art and science and relationships and joy that could have been but now will never be. The philosopher Derek Parfit explored these questions in his work on population ethics. He pointed out that our actions today affect not just currently existing people but all the people who might exist in the future. If we cause human extinction, we prevent the existence of potentially trillions of future people who might have lived good lives. From this perspective, existential risk isn't just about preserving current humanity but about preserving the possibility of all future humanity. And since the future could potentially contain vastly more people than currently exist, and last for vastly longer than history so far, the moral weight of the future is enormous. Consider, roughly 100 billion humans have ever lived. But if humanity survives another million years at current population levels, that's about 8 quadrillion people, 80,000 times as many. And a million years is nothing on cosmic timescales. If humanity spreads to other star systems and persists for billions of years, the number of potential future lives becomes almost incomprehensibly large. This is the perspective underlying what's called long-termism, the idea that positively influencing the long-term future is a key moral priority, potentially the key moral priority, because of the vast number of lives at stake. From a long-termist perspective, reducing existential risk becomes arguably the most important thing we can do, because existential catastrophe doesn't just harm currently existing people, it prevents all future people from existing. But this perspective is controversial. Critics argue that it could be used to justify sacrificing the well-being of currently existing people for speculative future benefits. If preventing existential risk is the ultimate priority, does that mean we should divert resources from helping people suffering today to instead fund asteroid detection or AI safety research? There are also deeper philosophical objections. Some philosophers question whether we have moral obligations to people who don't exist and might never exist. Others argue that quantity of lives isn't what matters, that a shorter civilization that treats people well might be better than a vastly longer one where people suffer. And there are troubling historical precedents of ideologies that claim to be serving the future or posterity while causing immense suffering to people in the present. We should be wary of arguments that always prioritize hypothetical future benefits over actual present harms. I don't think these objections entirely negate the importance of existential risk, but they're worth taking seriously. We need to find ways to care about the long-term future without becoming callous about present suffering. We need to work to prevent existential catastrophes without using that goal to justify cruelty or authoritarianism. Fortunately, I don't think these goals are necessarily in conflict. Many interventions that reduce existential risk also benefit currently existing people. Pandemic preparedness helps prevent future existential pandemics but also helps prevent smaller, non-existential disease outbreaks. Climate change mitigation prevents potential long-term civilizational collapse but also prevents nearer-term harms like flooding, heat waves, and agricultural disruption. Nuclear arms reduction reduces existential risk while also reducing the risk of smaller nuclear conflicts. There's also a strong case that we owe something to future generations simply as a matter of reciprocity and fairness. Previous generations made choices that benefited us, they created institutions, accumulated knowledge, developed technologies, and in many cases made sacrifices so that we could have better lives. Don't we have a similar obligation to future generations? This perspective doesn't require long-termism or utilitarian calculations about vast numbers of future people. It's simply the recognition that we're part of a chain of generations, inheriting from the past and bequeathing to the future, and that we should try not to be the generation that breaks that chain. Now let me turn to another dimension of existential risk that's often overlooked, the risk not of complete extinction but of permanent stagnation or value lock-in. Extinction is the most extreme existential catastrophe. Humanity ends completely. But there are other scenarios that might be nearly as bad from a long-term perspective, even though some humans survive. Imagine a scenario where civilization collapses and the survivors revert to a pre-industrial existence. Normally, we might expect civilization to eventually rebuild. Humans did it once, presumably we could do it again. But there's a troubling possibility. What if rebuilding industrial civilization is actually much harder the second time around? When humans first developed industrial technology, we had access to easily extractable coal and oil deposits near the surface. We had rich iron ore that could be smelted with relatively simple technology. We had dense forests for charcoal production. We had concentrated deposits of various minerals. We've now used up most of these easily accessible resources. The coal and oil we use today requires sophisticated technology to extract: deep mining, offshore drilling, hydraulic fracturing. If civilization collapsed and we lost this technology, could we rebuild it? The survivors of a collapse might be stuck in a sort of technological equilibrium, too advanced for Stone Age technology, but unable to reach the industrial stage because all the low-hanging fruit has already been picked by the first industrial civilization. They might have knowledge that industrial technology is possible. They might even have books or artifacts from before the collapse, but lack the accessible resources to recreate it. This is speculation, and some researchers argue that renewables like solar and wind power could provide a path to reindustrialization without needing fossil fuels. But it's a concerning possibility, a permanent reduction in humanity's technological potential due to resource depletion. There's a related risk called value lock-in, the possibility that certain values or ideologies might become permanently entrenched, preventing moral and social progress. Throughout history, human values have evolved. We've moved, haltingly and imperfectly, toward recognizing the rights and dignity of more people, the abolition of slavery, the expansion of political rights, the recognition of human rights across boundaries of race, gender, and nationality. This moral progress has been possible partly because no single value system could achieve complete dominance. Power was distributed across different societies with different values. Ideas could spread and compete. Oppressive systems eventually face challenges from alternatives. But imagine a future where a particular value system achieves global dominance and has the technological means to make that dominance permanent. Perhaps through sophisticated surveillance and social control, or through AI systems designed to preserve certain values, or through genetic or neurological engineering that makes people unable to question certain beliefs. This might not look like a catastrophe from the inside. If you agree with the values being locked in, it might even seem like paradise. Finally, the right values prevail forever, with no backsliding or corruption. But from a broader perspective, it might be a disaster. It would mean the end of moral progress, the freezing of human values at one particular point in history. And given that every previous era had moral blind spots that later generations recognized and corrected, it's almost certain that our current values also have blind spots we can't see yet. Locking in today's values would mean never discovering what we're wrong about, never progressing beyond our current moral limitations. We'd be like a species that reached medieval technology and then stopped, never discovering everything that came after. This risk becomes more salient as technology advances. A medieval king who wanted to make his ideology permanent across all humanity lacked the means to do so. But future technologies might make such lock-in possible. Let me explore another crucial but often underappreciated aspect of existential risk, the psychological and sociological dimensions of how we respond to these threats. Humans are remarkably bad at dealing with certain types of risks, and existential risks tend to have exactly the properties that make them psychologically difficult to process and respond to appropriately. First, there's the problem of probability neglect. Research in cognitive psychology shows that people tend to treat low-probability catastrophes irrationally. We either ignore them completely or treat them as if they're certainties, with very little middle ground. A 1% chance of human extinction this century sounds low. There's a 99% chance we'll survive. But if you think about it carefully, 1% is terrifyingly high. If you had a 1% chance of dying every time you got in a car, you'd probably never drive. If an airline had a 1% crash rate per flight, it would be immediately grounded. Yet when we hear about a 1% extinction risk, it's easy to dismiss it as unlikely, to focus on the 99% chance of survival rather than the 1% chance of catastrophe. This is probability neglect. Our emotional response doesn't scale appropriately with the actual magnitude of the risk. Related to this is the problem of psychological distance. Threats that are distant in time, space, or social connection feel less real and urgent than immediate threats, even if the distant threats are objectively more severe. Climate change is a perfect example. The worst effects are decades in the future and will primarily affect people in distant countries or future generations. Even though the aggregate harm is enormous, it feels psychologically distant compared to immediate concerns like paying rent or health problems or political conflicts. This psychological distance makes it hard to maintain sustained concern and action. We might feel worried about climate change when we read a news article about it, but then that concern fades as we return to our daily lives and immediate concerns. There's also the problem of diffused responsibility. When everyone is responsible for addressing a problem, it's easy for each individual to assume that someone else will take care of it. This is particularly acute with global existential risks, where action requires coordination across billions of people and hundreds of countries. Who exactly is responsible for preventing asteroid impacts? Or managing AI risk? Or reducing nuclear arsenals? There are various institutions and individuals involved, but the responsibility is so diffused that it's easy for everyone to assume someone else is handling it. This diffusion of responsibility is compounded by the free rider problem. Actions to reduce existential risk are global public goods. Everyone benefits if the risk is reduced, regardless of whether they contributed to reducing it. This creates an incentive for each individual and each country to let others bear the costs while still enjoying the benefits. If one country invests heavily in pandemic preparedness, all countries benefit when pandemics are prevented or contained. If one research institution solves AI alignment, everyone benefits from safer AI. This seems good, but it means that each actor has an incentive to underinvest in these global public goods, hoping to free ride on others' investments. The result is that we collectively underinvest in existential risk reduction compared to what would be rational from a global perspective. There's also what we might call the Cassandra problem, after the figure from Greek mythology who could accurately predict disasters but was cursed never to be believed. People and institutions that warn about existential risks often face skepticism, dismissal, or ridicule. This is partly rational. There are many false prophets predicting doom, so skepticism is warranted. But it creates a problem when the warnings are actually accurate. Scientists warning about climate change have faced this for decades. AI safety researchers often encounter dismissal from those who think the concerns are science fiction. People worried about pandemic risk were often treated as alarmist, until COVID-19 demonstrated that the risks were real. This creates a perverse dynamic. The people most concerned about existential risks are often marginalized or dismissed, making it harder for their warnings to translate into action. The problem is exacerbated by motivated reasoning and tribal epistemology. In polarized societies, beliefs about risks often become markers of group identity rather than being based on evidence. If your side believes climate change is serious, then my side must believe it's exaggerated, and vice versa. This tribal epistemology makes it nearly impossible to have rational conversations about risks. Evidence and arguments are filtered through the lens of group loyalty. Acknowledging that the other side might be right about something feels like betrayal. We've seen this play out repeatedly with COVID-19. What should have been straightforward public health questions, do masks reduce transmission, are vaccines safe and effective, should we restrict large gatherings during outbreaks, became tribal markers. People chose positions based on group identity rather than evidence, with predictably disastrous results. Now imagine trying to build global cooperation on existential risks in this environment. It's extraordinarily difficult. There's also the problem of temporal myopia. We heavily discount the future, valuing immediate benefits far more than delayed ones, even when the delayed benefits are much larger. Economists often model this with discount rates, but the psychological reality is even more extreme. People will often choose a small reward today over a larger reward next week, even though rationally the larger reward is obviously better. This temporal myopia makes it very hard to make sacrifices now to prevent harms in the distant future. Why should we reduce our consumption today to prevent climate change that will primarily affect people in 50 or 100 years? Why should we invest in asteroid detection to prevent an impact that probably won't happen for thousands of years? The rational answer is that the future matters and we have obligations to future people. But psychologically, the future feels unreal. It's hard to maintain concern for abstract future people when we have concrete present needs. These psychological barriers are compounded by institutional and economic structures. Companies are accountable to shareholders on quarterly timelines. Politicians face election cycles of 2 to 6 years. Media organizations chase daily news cycles. None of these institutions are well suited to addressing problems that unfold over decades or centuries. A CEO who invests heavily in preparing for risks that might materialize in 20 years will likely be replaced by shareholders who want better quarterly returns. A politician who asks constituents to make sacrifices now for benefits that will accrue to the next generation will likely lose to an opponent promising immediate benefits. This creates a systemic bias toward short-term thinking, even when everyone involved intellectually understands that long-term thinking is important. So how do we overcome these psychological and institutional barriers? One approach is to make the risks more psychologically vivid and immediate. Instead of talking about abstract probabilities, tell stories about specific scenarios. Instead of discussing harms to future generations, describe the effects on children and grandchildren alive today. Instead of presenting statistics, show images and videos that create emotional engagement. This approach has risks. It can lead to emotional manipulation and can sometimes backfire by making people feel overwhelmed and hopeless rather than motivated. But done carefully, making risks more psychologically real can help overcome probability neglect and psychological distance. Another approach is to create institutional structures that are specifically designed to represent long-term interests. Some countries have experimented with future-focused institutions, parliamentary committees dedicated to long-term thinking, requirements for impact assessments that consider effects on future generations, even proposals for giving formal representation to future people in political systems. These institutional innovations are still nascent and face many challenges, but they represent attempts to overcome the structural bias toward short-term thinking. We can also try to align short-term and long-term incentives. Investments in renewable energy both reduce long-term climate risk and create immediate jobs and economic opportunities. Pandemic preparedness both prevents future catastrophes and improves current public health. AI safety research both reduces long-term existential risk and helps make current AI systems more reliable and beneficial. By identifying these win-win scenarios, we can make progress on existential risks while also addressing immediate needs, helping to overcome temporal myopia and making it easier to build political support. There's also value in creating and strengthening global epistemic commons, shared spaces for evidence-based discussion that transcend tribal boundaries. Scientific institutions, academic journals, and international organizations can serve this function when they're trusted and properly supported. The challenge is maintaining trust in these institutions. This requires transparency, accountability, genuine engagement with criticism, and demonstrated commitment to truth over ideology. It's hard work, and these institutions are always imperfect. But they're necessary if we're to have any hope of coordinating global responses to existential risks. Education also plays a crucial role. If people understand basic concepts like probability, risk assessment, exponential growth, and systems thinking, they're better equipped to think rationally about existential risks. If they understand cognitive biases and tribal epistemology, they can recognize these patterns in themselves and others. This doesn't mean everyone needs to become an expert on every existential risk. But basic risk literacy, scientific literacy, and critical thinking skills are increasingly necessary for citizens in a world facing complex, long-term threats. Let me also address the emotional and existential dimension of living with awareness of these risks. It can be psychologically burdensome to genuinely internalize the reality of existential threats. Some people respond with denial or avoidance, they simply don't think about it, or they dismiss the risks as exaggerated. This is psychologically understandable but practically problematic, because these risks require active attention and effort to mitigate. Others respond with anxiety or despair, they become overwhelmed by the magnitude and severity of the risks, leading to hopelessness or paralysis. This is also understandable but ultimately counterproductive. Despair leads to inaction, which makes the risks more likely to materialize. The healthiest response, I think, is what we might call informed concern combined with active hope. This means acknowledging the reality and seriousness of existential risks without exaggerating or catastrophizing. The risks are real and deserve serious attention, but they're not necessarily inevitable. Recognizing that while individual action is limited, collective action can be powerful. No single person can solve climate change or prevent all existential risks, but together, coordinated action can make a meaningful difference. Finding ways to contribute that match your skills, resources, and circumstances. Not everyone needs to become an existential risk researcher. You can contribute by supporting relevant organizations, by voting and advocating for policies that take long-term risks seriously, by having conversations that help others understand these issues, by making career choices that align with addressing these challenges, or simply by living thoughtfully and encouraging others to do the same. Maintaining perspective and balance. Yes, existential risks are important, but so is living a meaningful life, cultivating relationships, experiencing joy, and appreciating beauty. Becoming so consumed with preventing future catastrophes that you can't enjoy or appreciate present existence is a form of failure. We're trying to preserve the future precisely because we value the kinds of experiences and relationships and meaning that life makes possible. This balance is delicate. We need enough concern to motivate action, but not so much that it becomes paralyzing. We need to think seriously about catastrophic risks without becoming morbid or nihilistic. We need to care about the long-term future while also valuing the present. Different people will find different balances depending on their personality, circumstances, and role in society. Someone working directly on pandemic preparedness or AI safety might appropriately spend more time thinking about existential risks than someone working in an unrelated field. What matters is that collectively, we're paying adequate attention and devoting sufficient resources to these challenges. Now let me turn to a question that's particularly relevant in 2026. What specific actions and developments should we be watching in the near term? For climate change, the next few years are crucial. The commitments made at recent climate conferences need to translate into actual emissions reductions. We should watch whether major economies are actually decarbonizing at the necessary pace, whether renewable energy deployment continues to accelerate, whether new technologies like green hydrogen and advanced batteries achieve commercial scale, and whether there's progress on hard-to-decarbonize sectors like aviation, shipping, and heavy industry. We should also watch for early warning signs of potential climate tipping points, major changes in ice sheet dynamics, significant shifts in ocean circulation patterns, or large-scale releases of methane from permafrost. The science here is still uncertain, but these would be red flags requiring immediate additional action. For AI risk, we're in a critical period. The capabilities of AI systems are advancing rapidly, and the next few years will likely see continued progress toward artificial general intelligence or systems with increasingly general capabilities. Key things to watch include Whether AI labs are taking safety and alignment seriously or prioritizing capability advancement over safety. Are they conducting rigorous testing before deployment? Are they transparent about risks? Are they cooperating on safety research or just competing on capabilities? Whether governments are developing effective regulatory frameworks. Are they creating oversight mechanisms for advanced AI? Are they requiring safety testing and certification? Are they fostering international cooperation on AI governance? Whether we're seeing early signs of misalignment or systems behaving in unexpected and potentially dangerous ways. Not every unexpected behavior is catastrophic, but patterns of systems pursuing unintended objectives or finding unexpected loopholes would be concerning. Whether there's progress on technical AI safety research. Are we developing better methods for ensuring AI systems do what we want? Are we solving problems like robustness, interpretability, and goal alignment? For biosafety and pandemic risk, COVID-19 has heightened awareness and led to some improvements in preparedness, but we should watch whether this translates into sustained investment and institutional reform. Are countries maintaining and improving disease surveillance systems? Are they investing in rapid response capabilities? Are they addressing the gaps exposed by COVID-19, like supply chain vulnerabilities and inadequate healthcare surge capacity? Is there progress on international cooperation for pandemic preparedness? The world's response to COVID-19 was fragmented and often counterproductive, with countries hoarding supplies and restricting exports. Are we building better mechanisms for coordinated global response? Are biosafety and biosecurity measures keeping pace with advances in biotechnology? As genetic engineering becomes more accessible, are we ensuring that dangerous research is properly contained and that potentially dangerous information isn't freely accessible? For nuclear risk, tensions between nuclear-armed states remain a concern. We should watch for signs of escalation or de-escalation in major conflict zones, for changes in nuclear doctrines or deployments that might increase risk, and for progress or setbacks in arms control agreements. The renewal or expiration of the New START treaty between the United States and Russia, the status of Iran's nuclear program, tensions between India and Pakistan, and the continued expansion of China's nuclear arsenal are all relevant factors. We should also watch for technological developments that might increase nuclear risk, such as hypersonic weapons that reduce warning time, cyber capabilities that might compromise nuclear command and control systems, or AI systems being integrated into nuclear decision-making. For space risks, we should watch for progress in planetary defense capabilities. NASA's DART mission successfully demonstrated asteroid deflection technology in 2022. But we need continued investment in detection and characterization of potentially hazardous objects and development of deflection capabilities. We should also watch for developments in space governance. As more countries and private companies become active in space, are we developing rules and norms that prevent conflicts and accidents? Are we avoiding the creation of debris fields that could make certain orbits unusable? Beyond these specific domains, there are some broader trends and developments worth monitoring. The state of international cooperation and institutions. Are countries becoming more or less willing to work together on global challenges? Are international institutions being strengthened or weakened? Is there progress toward better global governance, or are we seeing increased fragmentation and nationalism? The health of democratic institutions and civil society. Democracies are generally better at managing existential risks than authoritarian systems because they allow for open debate, public accountability, and course correction. Erosion of democratic norms and institutions is concerning. The state of scientific research and education. Are we adequately funding research on existential risks? Are we training the next generation of researchers? Are we maintaining strong scientific institutions capable of providing evidence-based guidance? The trajectory of global inequality and social stability. Extreme inequality and social instability make it harder to coordinate responses to collective threats. Are we moving toward more inclusive economic systems, or are we seeing increased polarization and conflict? the development of transformative technologies beyond those I've discussed. Nanotechnology, quantum computing, brain-computer interfaces, and other emerging technologies could create new risks or provide new tools for managing existing risks. Public awareness and concern about existential risks. Are these issues becoming more prominent in public discourse? Are they influencing political decisions and resource allocation? Or are they being crowded out by shorter-term concerns? These are complex, multifaceted issues, and monitoring all of them requires the work of many people across many institutions. No individual can track everything, but collectively, we need to be paying attention. Let me also address what individuals reading this might actually do, beyond just being aware of these issues. If you're in a position to influence resource allocation, whether in government, philanthropy, or business, consider directing resources toward existential risk reduction. This might mean funding research, supporting relevant organizations, or investing in technologies that reduce risk. If you're choosing a career or considering a career change, consider whether there are paths that would allow you to contribute to addressing these challenges. There's need for people with diverse skills, scientists and engineers working on technical solutions, policy experts working on governance frameworks, communicators helping to raise awareness, educators training the next generation, and many others. If you're involved in politics or policy, advocate for taking existential risks seriously. Support candidates and policies that demonstrate long-term thinking. Push for institutional reforms that better represent future generations. If you're a researcher or academic, consider whether your work could contribute to understanding or mitigating existential risks. This doesn't mean everyone should switch fields, but there may be ways to orient your work toward these challenges. If you're an educator, consider how to incorporate long-term thinking and risk literacy into your teaching. Help students develop the conceptual tools to think about complex, long-term challenges. If you're a parent, consider how to talk with your children about these issues in age-appropriate ways that cultivate concern without creating anxiety or hopelessness. Help them develop both awareness of challenges and confidence in humanity's ability to address them. If you're involved in media or communication, consider how to cover existential risks in ways that are accurate, engaging, and conducive to productive action rather than just fear or despair. And for everyone, stay informed, have conversations, support relevant organizations, vote thoughtfully, and live in ways that reflect your values and your concern for the future. None of this is to suggest that everyone should make existential risk their primary focus. People have many responsibilities and concerns, and a functioning society requires people working on many different things. But collectively, we need more attention and resources directed toward these challenges than we currently provide. There's also value in simply maintaining awareness and letting that awareness inform decisions large and small. How you vote, what you buy, what you support, what conversations you have, all of these are shaped by your understanding of the world and what matters. If you understand that we face serious long-term risks that require coordinated action, that understanding will naturally influence your choices and priorities. Let me conclude by stepping back and reflecting on some broader themes that emerge from thinking seriously about existential risk. First, there's the profound responsibility that comes with being alive at this particular moment in history. We are among the first generations to have the power to destroy ourselves, but potentially also among the last generations that face existential risks from our own limitations and mistakes. If we navigate the next few centuries successfully, our descendants might have the wisdom, technology, and coordination to make existential catastrophe extremely unlikely. This means we live in what might be called a time of perils, a bottleneck period where the future of humanity depends critically on the choices we make. Previous generations didn't have this responsibility because they lacked the power to cause existential catastrophes. Future generations hopefully won't have it because they'll have solved these problems. But we're in the middle, bearing the weight of determining whether there will be future generations at all. This is both terrifying and inspiring. Terrifying because the stakes are so high and the challenge is so complex. Inspiring because it means our actions actually matter on the largest possible scale. The choices we make about climate policy, AI development, nuclear arsenals, pandemic preparedness, and countless other issues don't just affect us, they shape the entire trajectory of Earth-originating intelligent life. Second, thinking about existential risk reveals deep questions about what we value and why. Why does it matter if humanity continues? What are we trying to preserve? The obvious answer is that we value human life and human experience, consciousness, relationships, beauty, meaning, joy, discovery, creation. We want these things to continue because they're intrinsically valuable. But there's also something we might call the cosmic perspective. We're the universe becoming aware of itself, matter organizing itself into patterns complex enough to contemplate existence. As far as we know, Earth might be the only place in the observable universe where this has happened. The emergence of life and intelligence here might be extraordinarily rare, perhaps unique. If that's true, then humanity's extinction wouldn't just be a tragedy for humans, it would be a cosmic tragedy, the universe losing its only chance, or one of very few chances, to understand itself. We don't know if this is true. The universe is vast, and there might be many other intelligent civilizations out there. But we also might be alone, or effectively alone given the vast distances between stars. And even if there are other civilizations, each one is unique and valuable. The art, ideas, relationships, and experiences that humans create are irreplaceable. If we go extinct, no other civilization, however advanced, can recreate exactly what we would have created. This cosmic perspective doesn't replace concern for individual human welfare, if anything, it deepens it. Each person is a unique nexus of consciousness and experience, irreplaceable and valuable. The cosmic significance of humanity is built from the accumulated significance of billions of individual lives and experiences. Third, existential risk thinking highlights our radical uncertainty about the future. We can identify various risks and try to estimate their probabilities, but there's deep uncertainty about both the risks we face and our ability to address them. There might be risks we haven't even conceived of yet, threats from technologies not yet invented, from natural phenomena we don't understand, from scenarios too strange or complex for us to imagine. The history of existential risk thinking is full of examples of risks that became apparent only recently. Nuclear weapons didn't exist as a concept before the 20th century. Climate change wasn't widely recognized as a serious risk until the late 20th century. AI risk became salient even more recently. What other risks are we missing? What will people 50 years from now look back on and wonder how we didn't see it coming? This uncertainty cuts both ways. There might be terrible risks we don't yet recognize, but there might also be solutions we haven't imagined. Technology and understanding that seem impossible today might become routine in the future. Problems that seem intractable might yield to new approaches or tools. This uncertainty is uncomfortable but also liberating. It means the future is genuinely open, not predetermined by current trends or apparent trajectories. Our choices and actions can shape outcomes in ways we can't fully predict or control, but that doesn't mean they don't matter. It means they matter enormously, even if we can't see exactly how. Fourth, engaging with existential risk requires holding multiple perspectives simultaneously. We need both urgent concern and patient optimism. We need to recognize both the severity of the risks and the genuine possibility of addressing them. We need both clear-eyed realism about challenges and imaginative vision about possibilities. This is psychologically demanding. It's easier to pick one perspective, to be either complacent or despairing, either dismissive of risks or overwhelmed by them. But the truth requires holding tensions, being worried but not paralyzed, being realistic but not nihilistic, being ambitious but not naive. We need what the poet John Keats called negative capability, the capacity to be in uncertainties, mysteries, and doubts without irritably reaching after fact and reason. We have to act despite uncertainty, to commit to long-term efforts despite not knowing if they'll succeed, to care deeply about outcomes we can't fully control. Fifth, existential risk thinking reveals the inadequacy of many of our existing moral and political frameworks. Most ethical systems were developed to address individual actions and their immediate effects on other individuals. Most political systems were designed to manage conflicts within bounded communities over finite timescales. But existential risks require us to think about actions that affect billions of people across centuries or millennia, about probabilities and aggregated consequences rather than individual intentions, about coordination across the entire species rather than just within communities. This doesn't mean our existing ethics and politics are useless, they contain valuable insights and principles. But they need to be extended and adapted to handle these unprecedented challenges. We need what might be called an ethics of the long-term future and a politics of planetary coordination. Developing these frameworks is urgent work. We can't wait until we have perfect theories before acting, the risks are too pressing. But we need to be simultaneously acting on current best judgment and working to improve our conceptual and institutional tools for addressing these challenges. Sixth, there's a tension between individual powerlessness and collective agency. As an individual, you have very limited ability to influence global existential risks. You can't personally stop climate change or prevent AI catastrophe or eliminate nuclear weapons. This can feel disempowering and lead to resignation. But collectively, humanity has enormous agency. We created these risks, which means we can also address them. We have the knowledge, technology, and resources needed to make extinction much less likely. What we sometimes lack is coordination, political will, and sustained attention. Bridging this gap between individual powerlessness and collective agency is one of the great challenges of our time. It requires institutions that can channel individual actions into collective outcomes, communication that helps people understand their role in larger systems, and political structures that enable coordinated action on shared challenges. It also requires individuals to embrace their limited but real agency, to take whatever actions are available to them, however small, that push in the right direction. Cultural change happens through millions of individual choices and conversations. Political change happens through individual votes and advocacy. Resource allocation happens through individual decisions about careers, donations, and purchases. No individual action is sufficient, but each contributes to patterns that shape outcomes. We need both humility about our individual limitations and recognition of our collective power. Seventh, engaging seriously with existential risk is ultimately an expression of love for humanity, for life, for the magnificent improbable fact of consciousness and meaning in the universe. It would be easier not to think about these things, to focus only on our immediate concerns and pleasures, to assume someone else will handle the big problems. Choosing to engage with existential risk means choosing to bear the psychological weight of knowing about these threats and the responsibility of trying to address them. Why do that? Because we care. Because we think the future matters. Because we feel some responsibility to the generations who came before us and invested in creating the world we inherited, and to the generations who might come after us if we succeed in passing on a livable world. This care, this love, is what makes us human in the deepest sense. It's what makes us capable of acting not just for our own immediate benefit but for abstract others, future people, distant people, all the possible lives that might flourish if we navigate these perils successfully. So let me end with something perhaps unexpected: hope. Yes, we face serious risks. Yes, the challenges are immense. Yes, there's genuine possibility of catastrophe. I haven't been exaggerating or catastrophizing in this discussion. The risks are real and the stakes are as high as they could possibly be. But we're not helpless. We have agency, knowledge, and resources. We've solved difficult problems before. We've created international institutions, developed powerful technologies, coordinated action across billions of people. We've eliminated diseases, prevented wars, solved coordination problems that seemed impossible. We can do this. We can reduce existential risks to manageable levels. We can create a future where humanity not only survives but flourishes, spreading through the solar system and beyond, creating art and science and meaning on scales we can barely imagine, ensuring that the story that began with the first replicating molecules billions of years ago continues for billions of years into the future. This is possible. It's not guaranteed, nothing is guaranteed. But it's genuinely possible, and that possibility is worth fighting for. The fight won't be easy. It will require sustained effort across generations, coordination across cultures and nations, wisdom in developing and deploying powerful technologies, and constant vigilance against complacency and short-term thinking. But this is the work of our time. This is what history and circumstance have given us to do. Future generations, if they exist, will look back at this period as the time when humanity either rose to meet its greatest challenges or failed to do so. I believe we can rise to meet them. I believe that awareness, effort, intelligence, and cooperation can make a future not just possible but likely. I believe that the same capacities that created these risks, our scientific knowledge, our technological power, our ability to coordinate on large scales, can also be turned toward addressing them. The story of humanity doesn't have to end in this century or the next. It can continue for thousands, millions, even billions of years. All the art not yet created, all the discoveries not yet made, all the lives not yet lived, all the experiences not yet had, all of that is possible if we act wisely and well. That's what's at stake. That's why this matters. That's why, despite the difficulty and uncertainty, we must engage with existential risk not with despair but with determined hope. The future is not yet written. We're writing it now, with every choice and action, individual and collective. Let's write a future worth living, a story worth continuing, a cosmic adventure that honors the improbable magnificent fact that we exist at all. Thank you for taking the time to think about these issues with me, Josu. The fact that you're reading this, engaging with these questions, thinking about the long-term future, that matters. That's part of how we collectively navigate these challenges, through millions of individual minds grappling with these questions and choosing to care about what happens next. The work continues. The future awaits. Let's make it a good one.